Before class, you should review section 1.A. It's a discussion about complex numbers, and everyone should know what those are, but there's the set definition that you see in front of you here. And of course, I is our square root of -1 that we've come to know from high school algebra class. Often we're going to use this notation to discuss or label complex numbers. And the way we visualize that, just to point this out, is that we think about a complex number in much the same way that we think about a Cartesian coordinate system when we're trying to visualize it. So we think of associating to the complex number z, let's call it. It's an a plus bi, where a and b are real numbers. And so we can think about labeling that in the form of a little vector or a little point in R2, for example. And we can do that if we label the horizontal and the vertical axis according to the real part and the imaginary part of any number, any complex number z, like you see here. And so then when we think about labeling the point AB, we see the point on the x-axis or the horizontal axis and the point on the vertical axis labeled AB. Often we call those things the real part of the complex number and the imaginary part of the complex number. And this is a visualization that can help us understand a little bit more about the way that complex numbers work, and in particular, how to visualize addition and multiplication, what that means. And so go through and read your textbook, the proper definitions of how you add and then how you multiply two complex numbers together. Those two operations satisfy several properties, and I've written them down very briefly here. Take a look at those on page 3 of your textbook. It's the standard stuff from your algebra that you learned probably in middle school and high school: commutativity, associativity, the identity with respect to addition, the identity with respect to multiplication, additive inverse, multiplicative inverse, and distributive property. I'm not going to go through those here, but please review those before we get started in class. Now, I do want to point out that once you have all these properties, the consequences of that, the fact that you have an additive inverse, the fact that you have a multiplicative inverse, those things allow you to define these other operations, if you will, or way of thinking about things in terms of subtraction and division. One other thing I'll point out to reinforce here is that you know from classes before that R and C are what we call fields. And in this class, we're mostly going to deal with R and C, the real numbers and the complex numbers. Generally, many things are going to be true whether you're working with R or C. And so we're going to call our scalar field F, just like the notation that you see there. Often what's going to happen is only in certain places are we going to even have to worry about whether we're dealing with real numbers or complex numbers. And possibly in other classes, you've used other fields. Generally, we're going to stick with these two in this class. What I would say at this point is be sure that you review all of the properties that you know about R and C, techniques for visualizing things. It's in my notes, but I'm not going to discuss it in class. I think it's something you can review on your own, but make sure that you think about how we're going to graph or visualize or sketch pictures for vectors and addition and scalar multiplication of elements of this class. One definition that I do want to spend a little time on, maybe I should move this down just a little bit. The definition of a list. So this is in your textbook as well, and this will be really important for us going forward. So n's going to be a positive integer, and we are going to refer to a list, and in particular a list of a certain length, so of length n here. It's going to be an ordered collection of elements of some set, okay? And those elements are going to be separated by commas, and it looks like this. So each x1, x2 through xn, that's just our label for all of our different elements of our set that we're going to be working with. And we have separated those by commas, and then we've put parentheses around them. This is what we are going to refer to as a list. A list has a length associated with it. That is the number of individual elements that are separated by commas. And it's important to note that two lists are equal if they have the same elements and they have the same length. And I would refer you back to your textbook for a couple of examples of how we think about a list and distinguish it from a set. Couple of things. Each list has a finite length. In particular, notice in the definition, the n here was a positive integer, so that means it's a finite integer. So each list has a finite length, and often a list of length n is called an n-tuple, and you probably remember that from another class as well. The other thing is that a list of length 0 is denoted with these empty parentheses. That will be important a few times when we're going to make some distinctions in the class. Some other things that I would suggest at this point, please review definitions for something called fn, where n is a positive integer. That positive there doesn't look very much like a plus. Let's fix that as we move along. This is a better plus. Okay, so make sure you go through the definition of fn, where n is some positive integer. The definitions of addition and scalar multiplication on fn, I'm not going to cover them in class because I think a lot of people are going to be familiar with those. Also, before I move to section 1.b, a few words. Please remember there is a handout associated with this video or this little set of videos. Be sure to download that video, that handout, look at it, print it out, and have it in front of you before you watch the next part of the videos. Bring it to class to refer to. It's a nice reference sheet